Hi everyone, my name is William and I'm going to be sharing a little bit about Maglev, which is basically a train technology system. And so I'm going to try and talk a little bit about the science behind the system of Maglev, and then also talk about sort of the origins and history, and then about contemporary and future projects. So let's get started by talking a little bit about the science that is behind Maglev. Um, there are many different systems for Maglev transportation, but I'm going to try and focus on the system that's used in Japan right now because they've done the most research and their system is most prominent, and they have so many future projects that are coming that are exciting. So they use a system that they call electrodynamic suspensions. And basically the idea behind this is that by moving this magnet that you see down here, this electromagnet, through some coils below the carriages of the train, they will basically induct current, and by changing the magnetic field. And so by doing this, the poles are repelling and basically just pushing the train forward. And so you'll see also in this diagram that basically the train is levitating. It doesn't touch the track. And that's another really important part of maglev. So because of this induction current, the train moves without any force. There's no friction associated. And because it's not touching the tracks, so it doesn't need any force to move it forward. I'll now try and make some brief comparisons to standard systems of maglev. So there's no rotating friction between the wheels and the track on a maglev system. And basically, when there's no friction, it means that the train can travel at a faster speed much more easily. So maglev trains can reach speeds that conventional high-speed rail systems cannot even come close to. So if you look at this little diagram on the right, which is a comparison in Germany of maglev systems, you'll see that the energy used to go the same speed at 125 and 185 miles per hour, it requires much more energy for the conventional ICE train than the maglev system. But when we get to 250 miles per hour, we see that this speed, which can be achieved by maglev, can't even be achieved by the conventional high-speed rail. So it's very unique in that you can get to these speeds of 250 plus miles an hour using the maglev technology. However, there are some challenges with maglev compared to conventional. For example, you need supercooled magnets to have the superconductivity, and these are really expensive, and maintenance in general for maglev systems is a little bit difficult because they're so uncommon that what happens when you have a part that is broken or needs replacing is that you literally have to create a new part, because you know, there's not just like a parts dealership that has you know, 300-mile-an-hour maglev train equipment. It's so specialized that it's very difficult to find parts for these things. And the other thing is that it requires new infrastructure, right? You have to incur these very high startup costs and high maintenance costs for the first few years to literally build new tracks, right? Between all of your different locations that can serve a maglev train. However, we'll see that throughout the years, there have been some successes in terms of how they did that and how they approached startup and maintenance costs. So let's talk a little bit first about the origins of maglev and sort of earlier projects that have happened. So the first patent for maglev was actually awarded in 1905. So essentially, the mayor of Cleveland intended to build a wheelless railway. And so some scientists had come up with some ideas, and the mayor of Cleveland wanted to get on board. So in the early 1900s, they tried to do this, but it was kind of a flop. They didn't even fully develop the technology. There was not enough interest from the general public and from investors and the scientific community. So then 60 years pass by with little improvement in the technology. And there are a couple reasons for this. First, it's just very expensive to do R&D, as I'm sure many of you know. And then also two world wars, but a little bit of a damper in that. Obviously, technology and research and development became so much more focused on preparing countries to fight in World War One and then later World War Two, that they were focused more on tanks, um, war planes, things like that, which were not involved with the kind of conventional mass transit of people. However, after the war, during Japan's post-war economic miracle, they committed to developing maglev technology and have been doing so ever since. So they've dedicated their best and brightest scientists on this, and they've been testing different systems for maglev and how to perfect the maglev technology for a very long time, and actually have a 20-mile long maglev track to do testing at, where they've reached some really interesting conclusions. As for mass transit using maglev, this was used in 3 different cities in Europe: Hamburg in 1979, Birmingham in 1984, and Berlin in 1989. However, all of these systems came to a halt after only a couple years. The governments that operated them found that they worked just fine. This is a train that was used in Hamburg, by the way, for a maglev system, but that they were just too expensive to maintain. However, we'll see that there have been improvements in maglev over time that may make their use for commercial use more worthwhile. So now we'll talk a little bit about contemporary projects of maglev. And the only maglev system that's in use for transporting passengers for commercial use today is the Shanghai maglev, and it just has 2 stops. It travels from Pudong Airport to Longyang Road Station in Pudong, and it reaches 268 miles per hour over its journey. However, there is one problem, and that's that this train incurs significant losses. So they still get fare revenue, but it's not enough to break even. And so the government has to heavily subsidize the project to make sure that it stays afloat. Meanwhile, in China, there are many services related to maglev that are being expanded. They're trying to bring maglev at slower speeds to different cities. Eventually, they hope to get up to about a dozen metropolitan areas of service with maglev. Meanwhile, in Japan, there are ongoing tests, as there have been for over 50 years, to continue developing the technology of maglev. And actually in 2015, a test in Japan on that track I mentioned reached 375 miles per hour, which is much faster than conventional rail will ever be able to transport passengers. And so the idea that you can travel 375 miles per hour in a train, if you can get that train to travel in a straight line, is quite revolutionary and quite impressive. So if you think about your typical commute, intercity commute on a highway, for example, from Portland to Seattle, the average car without traffic will travel between 60 and 65 miles an hour. So if you can reach 375 miles an hour, you have the potential to reach your destination 5 or 6 times faster than you would in an automobile. So it's a very unique project, and it's very exciting to see where it's going. Now, in terms of the future of maglev, as I mentioned, there are many projects in China that involve expanding maglev, but these are at speeds that are more comparable to conventional rail and also to automobiles. They're looking at sort of 60 to 100 miles an hour range for intra-city transit. So looking at moving people within one metropolitan area. However, the L0 train in Japan is really exciting, and they plan to open this new system in 2027, although it's unclear how COVID-19 and other factors will affect the sort of development timeline. And they plan on operating this project from Tokyo to Nagoya first in 2027, and then 10 years later, opening the line from Nagoya to Osaka. So currently the bullet train travels from Tokyo to Osaka at less than 250 miles an hour. And the Japanese government and many civilians have been lobbying to try and, create basically an ultra bullet train. And Japan decided to use maglev technology to try and approach this issue. So here's the train that they have that this model is what they're going to use in 2027. And it plans to operate at 310 miles per hour, which is very unique and would be the fastest commercial train service to have ever operated. So in terms of sustainability, the outlook is good for maglev. Maglev will be increasingly seen by different governments as an option to turn to in the face of climate change when we think of how we can move people in a more sustainable way, but also a very efficient way, which is actually much faster than cars and in many cases airplanes in terms of time to travel to the airport and go through security and stuff. Many cases show that a maglev train that can operate at over 300 miles an hour will get you to your destination faster. So the future for maglev looks good, but we'll have to wait and see what happens with Japanese and Chinese projects, which seem to be kind of the bright and shiny future of maglev. Regardless, I'm really excited to see what happens, and I hope you all find kind of a newfound interest in maglev and transportation technology after this. So thank you all so much for listening, and thanks for the opportunity to let me create the video, and take care, everyone.